We got it right. We still have to turn it.
Sorry?
If we got it right, do we still have
Nope.
to turn it?
You're good. I think I looked yesterday. I think we have 6 classes left, and then we have the final after that. So let's see here.
Yeah, like the last question on the test.
You know what? I think they're on my desk. Yeah, I think there's 3 of them sitting there. It was for the students that weren't here that day. So, are you done after this today, or you got more? We might, if there's time, might be able to just swing by my office and pick it up if you want. It's like after class. Yeah. Yes. Yep. We'll just have to go real quick because I have another class that starts right after this one. Okay. Thank you. Do you have the test also? Okay, let's get started. So we're kind of in the final stretch here, right? And we're going to be starting chapter 13. Y'all ready to be done? All right, so chapter 13. Chapter 13 is called Integration. Integration. All right, so let me explain what's going on here. What we've done so far, one of the main ideas of this class has been if we start with a function, right, then we can do this thing called taking the derivative of it and turning it into f prime of x, right? And this operation of starting with the function, taking its derivative, is called differentiation. Okay, so we've learned how to differentiate different types of functions. And we've seen how we can use those in business to figure out, how fast something's going up or down at a certain point in time. So let me give you a specific example underneath this. If someone gave you the function f of x, we'll do something very simple. X to the 4th plus 3x squared. Then if we differentiate it, we get f prime of x, which is 4x cubed plus 6x. Right? So that's fine. Now this answer over here, this answer is just a function, right? This is a function, 4x cubed plus 6x. So imagine that we didn't know where this function came from. Imagine that we were just given this as a function to start without knowing that it came from this after taking a derivative. And we were asked, or we were told, that this is the derivative of something. Do you think that you could go from here back to there? I mean, there's got to be some way to do it, right? I mean, there's a way to go from here to here, so there's got to be a way to go backwards. And that's what the operation is that we're going to be talking about now. It's called integration, and it's going the opposite direction. Okay, so if we were to actually go and reverse this arrow to go the other direction, this is called integration. Understand? It's just backwards from what we've been doing. All right, so let's see if we can't come up with a couple of rules that will help us go backwards. And we'll start off with, again, Yes, the one that we started with when we were doing differentiation. So do you remember this rule? Recall that if we had x to the nth power and we took the derivative, that n came down and then we subtracted 1. So that was called the power rule for differentiation. That was the power rule. We just used that, didn't we, a second ago? X to the fourth, 4 came down, x cubed. Right? So we have a lot of experience with that. I wonder if there's a rule like that for finding, doing integration. What do you think? Do you think there's some sort of rule that would help you go backwards? Yeah. So let's try and see if we can't come up with the rule on our own without actually just me giving you the rule. Let's try it. Let's see if we can do it. So let's start here with an example. Let's say we have a function, and let's say it's 4x cubed. Find what is called the antiderivative. Now I have not told you what that means, antiderivative. What this is saying is integrate, right? We want to integrate. We want to do integration. We want to go backwards. So instead of finding the derivative, I want you to find the antiderivative. Understand? Antiderivative, opposite way. Okay? So this is some new language. So what would the antiderivative of this function be? X to the fourth, right? X to the fourth. Because if you take the derivative of x to the fourth, this is what we get. So how do I write that? Well, the standard notation for this is to write, instead of little f, capital F of x equals x to the fourth. This would be our answer. You'll agree with that? Now, I have a somewhat more profound question. Is that the only answer? Is it possible that there is another function that when we took the derivative of it, we could have still got this? What? Give me. Okay, so you could have tacked on like +3 to this and it would have worked. Let's see. Let's see if we all agree on that. Would this have worked? Would that have been a correct answer? Yeah, because when I take the derivative of this, I still get the 4x cubed, right? Then plus the derivative of 3, which would have been 0. So that would have worked also, right? Yeah, so we could do that with any number, right? We could have done like, +10. We could have done -7. There are an infinite number of actual antiderivatives. And that kind of creates a little bit of a problem. But do you get it? So these are specific examples of antiderivatives. I'm sorry, I'm having a hard time talking here. F of x equals, how about I write this? X to the fourth plus c. And box that. Wouldn't that kind of represent all the possible answers if c is a constant? So I'm assuming here c is just a number. Then this would cover all the different possible answers out there, wouldn't it? So this right here is called the general antiderivative. Okay, that's the general antiderivative. So if somebody just gives you a function and asks you for the antiderivative, there are an infinite number of them. So what we do is we just write the general antiderivative that covers all of them. Right? This covers every one of them. Any questions on that? Let's try another one. All right? Let's try another one. All I'm going to do is just tweak this problem just slightly. I'm going to take the 4 out. Okay. So let's start thinking about this a little bit. I guess instead of just recognizing like 4x cubed I had up there a second ago, instead of just recognizing, oh yeah, that's a derivative of x to the fourth, let's actually think about what's happening when you take a derivative, right? When you take a derivative, the power comes down by 1, right? So when you do the antiderivative, that power should go up by 1, yes? So when I look at this one right here, and I want to find the antiderivative, those are the instructions. I know it's going to be a function where I have x to the fourth. Now I'm going to leave a space in front of it for a reason. I know it's got to be x to the fourth, right? But it can't just be x to the fourth, because if I take the derivative of this, I get 4x cubed, right? And that's not what I have here. So if I took the derivative of this, this 4 would come out, and I don't want that 4 to be there. Right? I want that 4 to kind of get killed off. So what could I put out here in front that would help kill off that 4 that's about to come down? 1/4. Or you could put the whole thing over 4, but I'm going to place it out front. I'm going to put 1/4 out in front, so that's like multiplication in front. And do you see how that 1/4 is going to have the effect of killing the 4 off when it comes out? Yes? You sure? You look like, you're all right?
No, I got it.
You're okay? Okay. You got it? Okay. Everyone good with that? So, one more thing. Plus c, that will cover all the different constants I could throw out there. And you could just check this for yourself right now. Bring the 4 out. 1/4 the 4 is 1, so that would be a 1 out there. There's a 1. And then the power comes down, so that works, right? Okay. Let's try something else. Same problem, just going to tweak it a little bit. I'm going to put a 5 out here. Okay? So let's try that one now. So do you remember what happened when we took derivatives and we had constants out front? Right? What did we do with them when we took derivatives? If we had a constant, we brought them along for the ride, didn't we? So when we go backwards, we can also bring the constants along for the ride. So when you look at this problem right here, what I want you to realize is that we know that we need an x to the fourth still, right? We know that this 5 is going to come for the ride, backwards. But we still need to kill off that 4 when it comes down. So we still need the 1/4 out here. Y'all agree? And one more thing, plus c. Now, 5 times 1/4 is 5/4. I wouldn't leave it like this. So I would write 5/4 x to the fourth plus c. So if we want to check this real quick, if we took the derivative, the 4 would come out. It would be 5/4 times 4, x subtract 1 from the power is 3. The 4's would cancel, and you get 5x cubed. Y'all see it? Y'all all right? Y'all okay? All right. How about we do something a little different? So same instructions. How about x to the negative 3 instead? All right, so the idea here again is that if we have a power like this, we know that when we do the antiderivative, the power is not going to go down by 1, it's actually going to go up by 1, right? So I know that my antiderivative, capital F of x, should be x to what power? Negative 2. Not negative 4, right? Because this is negative 3. If you increase the power by 1, if you add 1 to that, that becomes negative 2. right? So this is going to be negative 2. So will that work like that? No, because when I take the derivative, that negative 2 is going to come down. So I don't want it there. So what do I put out front?
A negative.
Negative 1/2. If you want, you can look at that as being negative 1 over negative 2. That's really what we're doing.
Would we were wrong if we put the negative 2 at the bottom?
Yeah, this would be correct. This would be all right.
Like if I put x to the power of negative 2 all over.
All over, oh, you're asking could you write it this way? X to the power of negative 2 all over negative 2, like that?
Yeah.
That is okay. Now there's a reason why I don't do that. It's just because of,
It's easier to see it first.
well, the fractions out front, sometimes you have to put these together with other numbers, so it's just, for me, it's easier when they're all out in front of the x. But this is correct. I mean, this is not wrong. Because all you're doing is this. You're treating this right here as like this over 1, and you're just multiplying straight across. And you get 1 times this, which is the top, and the negative we'll put on the bottom, negative 2 times 1, which gives you negative 2. Okay, so hold on. Let me get to our final answer. This is where we were, right? Like that? I'm missing something, though. Plus c. And we're going to have plus c on every single one of these answers. Every single antiderivative has a plus c in it. And we actually call this has a special name. This is actually called the constant of integration. It's like anytime you do integration, you always get this constant. And so that is the constant of integration. All right. You ready to do another one? Let's try this. Do y'all feel comfortable so far? Because I want to give you something that's a little more difficult. What's the antiderivative of this? All right, the first thing we need to do is see if we can't wrap our heads around what this is. Like, is this x raised to a power? Okay, so square root means raise x to the half. Do you all agree with that? So before I even do any antiderivative, let's just make sure we all understand that this really means this. Right? Now, in order for me to use this rule, right, even when I did the power rule, I could not have this x down in the denominator. I had to bring it up to the numerator. So if you have x to the half on the bottom, can you rewrite that as x to a power where it's no longer in the bottom? Negative 1/2. You make it a negative power. Y'all okay with that? Okay, so that is just me rewriting the original function. I think at this point we can start looking at what the antiderivative might look like. I can tell you right now there's a 7 there, right? Because that's a constant in front. It can come for the ride. I can also tell you there's a plus c here because I'm doing integration. It's always going to be a plus c, right? And now what I need to do is figure out what the power on this is going to be. I need to add 1 to that, don't I? So maybe I do that on the side. I do negative 1/2. I need to add 1 to that. So if you're going to add those two together, you have to get a common denominator. So you have to rewrite 1 as 2 over 2, and then add these up. So what does this add up to be? You do negative 1 plus 2, so 1 on top and 2 on the bottom. You get a half.
So would it just be
Okay, so now I have this. I know I'm going to have x to the half power. Is that okay? Still good? Now, when that half comes down, I want it to go away. So how are you going to do that? I saw someone say 2. I agree. 2 will work. But really, what we've been doing in the past, like when we had x to the 4th, didn't we put 1/4 out here? Yes? And when we had x to the negative 2, didn't we put 1 over negative 2 like that? So we were always taking whatever this power was and we were putting it underneath the 1. Make sense? So technically speaking, what I'm doing is I'm doing 1 over whatever this power is, so like 1 over a half, like that. I know that looks weird, but 1 over a half, if the half comes out, won't it cancel? Okay? But what is 1 divided by a half? So if you have 1, how many halves go into it? 2, right? Or you could just say, when you have a fraction underneath a fraction like this, that this fraction flips and reciprocates up. So it becomes 2 over 1 instead of 1 over 2. Yes?
Could you just, instead of writing 1 over 1 half, could you just put a 2?
Yes.
Okay.
You could, but I wanted you to see this pattern that we've had. Whatever this power is, we've always put 1 over that power, right? Whatever the power is, 1 over that. Because I'm about to give you a formula like this, and that's the way the formula is going to be written. So we recognize right now that 1 over a half really is 2. So I'm going to write 7 times 2 times x to the half plus c. Right, that's where I am so far. And then what is 7 times 2? 14? 14, and then watch this. X to the half, I switched it back. Doesn't that mean the square root of x? So I just did 14 square root of x plus c. There's our general antiderivative. That's okay. So that was a little more involved, yes? All right, I think we're ready for the rule. Let's see if we can't come up with we're going to have what's called the power rule right now, but for integration, not differentiation. So let's see if we can do it. We'll put it as an example. So what if you have a function and it's x to some power? What would the antiderivative be? Well, that much I know, right? And then x to what power? 1 more than that power, right? So n plus 1. So it's just going to be x raised to whatever that power was plus 1. I don't know what that is, but it's 1 more than what it was, right? And then what do you need out front so that when this comes out, it kills it off? 1 over n plus 1. So I'll illustrate this again over here. When we had x cubed, that became 1/4 x to the 4th, right? When we had x to the negative 2, this became 1 over, oh no, it was x to the negative 3. It became 1 over, it was that. Okay, so when we had x cubed, when we took the antiderivative, we took x, we added 1 to the power, and then we did 1 divided by that power. Here, added 1 to the power, 1 over that power. When we had x to the negative 1/2, we added 1 to the power, and then we did 1 over that power. So there's the pattern. Do you see it? That's why I did it this way instead of writing 2. Right? So this is it. This is the power rule for integration. Can anybody, just by looking at this, tell me where we might run into a problem? If n is a particular number, this formula is not going to work. -1. If n is -1, this formula is not going to work. Because look, if n is -1, what's -1 plus 1? You get 0, and division by 0 is not allowed. So next to this formula, what I'd like for you to do is put if n is not equal to -1. All right, this is our formula for finding the antiderivative of a function. Any power function, we can find the antiderivative of it, so long as it's not -1. So what if it is? The formula won't work, right? So let's take a look at what is the function when you have x to the -1? What is that really? X to the negative 1 really means what?
1/2
1.
times x.
Negative exponents mean you can drop it down, right? So isn't this really just the function 1 over x? Isn't that the function 1 over x? Right? So do you remember what function we had that when you took the derivative of it, you got 1 over x? Natural log. Okay, so this is a special case. The antiderivative of this is the natural log of x plus c. And that's because we remember when we were taught what's the derivative of natural log of x, you were told it's 1 over x, right? So now if you're given 1 over x and you're asked to find the antiderivative, it goes back to natural log. So with these two things combined, this covers all powers of x. You can take the antiderivative of x to any power. Okay? All right. I'm going to give you a problem to work on and see if you can't get it. All right? I'll leave this up here just for now. So you try this one. I have a function here, f of x. It's x to the 7th minus 2 over x squared plus the cube root of x.
Are you trying to kill us?
I'm not trying to kill you. I'm trying to test your understanding. And then let me see. Oh, this one. We haven't talked about this. Plus 3. We'll see how you handle that. So I have some good news here. Do you remember when we took derivatives that when you had pluses and minuses, you did them individually? Yes? Antiderivatives work the same way. If you have pluses and minuses, you do them individually. So really what I've given you is 1, 2, 3, 4 separate problems to do here. Right? Each one of these is x to a power. And you need to apply this rule. This last one, don't overthink it, okay? Don't overthink it. But work on the first few first, all right? So let's see how the class does with this. Raise your hand when you're done. I'm going to go get a Kleenex. I'll be back. All right?
It'll be
Yeah. No Or you're, yeah, you're gonna find.
I think this will work. Yes. The second one, right here.
Down. So do you leave it as that answer?
Or put the x on the bottom.
Well,
Is that what
that's
you
I
mean?
was wondering, like, did you want it like natural log? Because you put
Oh, no,
natural
no.
log on the last one. So
We already took the antiderivative.
that's what I was wondering. 'Cause
Yes.
I was like, that would be another.
Yeah, that would be another one. No, we are done at that point. Yep. Okay, so I put the solution up here on the board to see if you can follow it. How many of you feel okay with this? Any questions on any particular parts? Now's the time.
Really just on,
What part?
I was gonna say really just on 2, but you kind of already explained it.
This one right here?
Yeah.
Okay, so the original function was -2. That's going to come for the ride. We have x to the -2. So what I need to do is add 1 to that, right? So I'm going to do 1 over whatever that power is plus 1, x raised to whatever that power is plus 1, right? So when I do this, -2 plus 1 is -1. 1 over -1 is -1. So when you multiply these two together, this is -2 times -1. So that's really positive 2. Now the power becomes -1, and we are done. We've already taken the antiderivative, so we don't have to do it again. If we did, if someone told us take the antiderivative of this again, you would have a natural log at that point. How about with this 1/3? What do you got?
I just have a question of how 1 over 4/3 turns into 3/4.
Okay, glad you have a question. All right, so we're taking 1 divided by 4/3, right? That's really what we're doing. Okay, this is the same as 1 over 1 over 4/3. I know that that's weird, but that is what it is, right? And remember that when you take two fractions, this is back from old school days, if I told you to take 1 over 1 and divide by 4/3, that division is the same as multiplication of the reciprocal. So what you do is you turn this into 1 over 1 times, that's the old school multiplication symbol, times 3/4. So you flip the second fraction over. So that's what I've done here. Basically, instead of doing this divided by this, I forget that and I do times 3/4. So really, if you don't want to deal with all that mental crap, all you have to remember is if you ever have 1 over a fraction, it flips, okay? But that's technically what's happening, all right? Any other questions? I saw some other kind of looks. You all right? What do you got? Ah, okay, so where did the 3x come from? So this I didn't give you a formula for, right? But this one I think we can get if we just think about it. If you have 3 times x, what's the derivative? Right? What's the derivative of 3x? Just 3, right? So if we do the antiderivative of 3, we're just going to get 3x, which I didn't say anything about. I wanted to see how y'all did with that. So if you have a constant, if somebody gives you a constant and asks you for the antiderivative, what's it going to be? That constant times x, always. Make sense? So if this would have been, 10, right? Then this would have been 10x. If there's no x's attached to it, the antiderivative would just be slapping x next to it. That okay?
Plus C.
And then the plus c is just because we always do plus c. Yeah. Okay? Yes? All right. Let me just double check some things here. All right. Now I want to show you something that's somewhat amazing, all right? They don't cover this too much in the book, but I want to show it to you because I think it makes it seem like maybe this is useful. All right, take a look at this function f of x equals, let's just go with this basic function x squared. I'm going to graph this for us real quick. I would hope that you would remember that the graph of that function looks like this little parabola, goes like this, right? What I'd like for you to do is focus your attention on the point here at the origin, and let's go out to 2. And if we go to 2 and we plug 2 into this function, it's going to spit out this point here, and that point here is 4. Y'all agree with that? So here's a pretty profound question that we as human beings asked ourselves a long time ago. If you were to draw dotted line straight down, and then at the 0, imagine that there's a little, like you have an endpoint here at 0 and at 2. Here's the question. What is the area of that shaded part? That is a very difficult question. And it's difficult because it's not one of our standard shapes, right? Like if somebody gives you a rectangle, we all know that a rectangle, if this is your length and this is your width, the area is length times width, right? We've seen that before. In fact, we can do some more complicated shapes. Like if we have a triangle, right? If this is your base and if you know your height of your triangle, then the area of this is 1/2 base times height. There's a formula for that. And we can even do something complicated like a circle. If we know the radius of a circle, the area of that is pretty commonly known pi r squared. So those are some of our standard geometric shapes, and we know areas of them, right? But what if the shape gets complicated like this? This isn't a circle, this isn't a triangle, this isn't a rectangle. How do you find the area of this, right? And when you think about like the history of humans, okay, at some point, and we're not going to get into like a debate about evolution versus any creation or anything like that, but I hope that you would agree that at some point we started to put borders between each other. And we started to say, this shit's mine, that shit's yours, don't cross this line, right? I mean, like we started to like, this is, you know what I'm saying? We still do it right now. So when we were starting to break up land, sometimes the land was a very easy shape, and sometimes there was a river that would run through and it would have a curve to it. And so how do you actually determine the area of something that has that weird shape to it, right? I mean, this is a standard parabola, but imagine if I asked you a more complicated question like, you know, you have a curve that does something like that, and I ask you to find this area, right? Like that. That seems like a very tough question, right? It turns out that to do this, all you need is the antiderivative. That's all you need. Okay, now we're not going to get into a big, deep explanation as to why. You're just going to have to take it on faith. But if you wanted to know what that area was, here's what you would do. You're going to take the antiderivative first. Okay, you're going to find the antiderivative. What's the antiderivative of that function? Okay, x to the third, and what do I need out front? 1/3, right? And then I'm going to have plus c. Okay, so you find that, right? Then what you do is you take the second endpoint, 2, and you plug it in here. So what would you get if you plug 2 in there? 1/3 times 2 cubed. 2 cubed is 8, right? So 8/3, and then you have plus c, right? Yes? Then what you do is you plug in the other endpoint, 0. What happens if you plug 0 in here? You just get c, all right? The area of this region, that area, is equal to this one minus this one, f of 2 minus f of 0, which would be, this was 8/3 plus c, right? But then you take away c. And what do you get? 8/3. It's exactly 8/3. That's what it is. So look, if this were a rectangle, what would the area of that rectangle be? This rectangle right here. It'd be 8, right? 2 times 4, that'd be 8. The area of this piece right here is 8/3, which if you did that on your calculator, 8 divided by 3, you'd get like 2.666 forever. Okay? 2.666. That would be the area of that region. That's pretty amazing, isn't it? That it works out that way? Okay. Now, the reason why I'm doing this is because I'm about to give you some new notation. Because we need a quick, easy way to say, hey, give me the antiderivative. Instead of me writing down like, hey, find the antiderivative. Mathematicians like to use symbols. So I'm about to give you a symbol. But I wanted you to see where the symbol came from. What we do, the actual like workings behind this, that we're not going to get into, has to do with something called Riemann Sums. But basically what we do is we take this area and imagine we cut it into a bunch of rectangles. Okay? Imagine I do a bunch of rectangles like that. If I were to take I could find the area of each of these rectangles, couldn't I? Because rectangles just length, width times height, just add, and then add them all up, right? And this would give me an approximation, because I would have some error in there. Do y'all see like I would have little gaps in here? See that little gap? That would cause a mistake in my answer, wouldn't it? Yes? So a way to get a better approximation would be to do more rectangles, right? And the more rectangles I do, the better my approximation becomes. And maybe it's possible that I could have an infinite number of rectangles. And there is, if I allow myself to use the idea that I'm going to put n rectangles in there, and then I'm going to let n go to infinity. I'm going to use a limit. Remember when we talked about limits? So you somehow use limits to do this, and then you add them all up. So we're going to add up an infinite number of rectangles. And when we add things in math, we call that a sum, don't we? And does anybody know the Greek letter for S, or the Greek letter for capital S? That's your Greek capital S. It's called sigma. S, so, this is our standard alphabet, S, sum, right? I'm going to take a sum of all these rectangles and somehow get an answer. But if we change that to Greek letters, it's this. And if we use an infinite number of rectangles, this symbol changes to this. All right? Now this is what I'm about to put up on the board, and this is all you really need to know, is what this notation means. When you see this, it's telling you to find the antiderivative. All right? So here it is. If I just gave you this symbol out of nowhere with actually like no background to it, it just seems like just a symbol. But it comes from the idea of a sum. The sum comes from the idea of an infinite number of rectangles, which helps us get an area. That's where it all comes from. All right, here we go. Some notation. If we want to find the general antiderivative of f of x, we will write the following. That's what we'll write. That's the notation. That is telling you, find the antiderivative of the function f. Now, there are some things here, just so you know what they're called. This right here is called the integral sign. This right here is the function, right? That's the function. We call that the integrand. And this little dx you can pretty much ignore because we're not going to go too deep into this. But this is called the differential. That becomes very important later if you were doing more advanced calculus. But in this class, we are not going to care too much about what that differential, like how it works, all right? Or what it's there for. But it has to be there. OK, so as an example, the first problem I gave you today was to find the antiderivative of x to the fourth, right? So if I wanted to write that a different way, I'd do this. That's it. That's what I'd write. And that's telling you to find the antiderivative of x to the fourth. Wait, was it x to the fourth? Was it x cubed? It was what? The first one I gave you? Yeah. OK, well, let's go with x to the fourth. So what is the answer to this? What is this equal to? Careful? 1/5 x to the fifth plus c. 1/5 x to the fifth plus c. OK? That seem OK with you? Let's make sure. What is that equal to? Natural log of x plus c. All right, how about we do one we haven't done? That's just e to the x. E to the x was that very special one, right? When you took the derivative of e to the x, you got e to the x. So when you take the antiderivative of it, you just get itself. It's such a nice function. Plus c, though. You have to have the plus c. OK. How about this one? Now, don't be freaked out by the u's, OK? The u's are just like the x's, all right? Everything's going to be the same, except you're going to have u's in our answers instead of x's in our answers. We have a problem here. The problem is that we have division. Do y'all see this? And we have two terms on the top. You are not allowed to just take the antiderivative of each one separately. You cannot do that. Because the only time you can do them separately is when there's addition and subtraction between them, right? This is division. Do you remember how bad it was when we took derivatives with division? We had to do quotient rule, didn't we? Okay, there's no easy way to undo it. There's not an easy way to undo division to go backwards. In fact, that's what makes Calculus 2 very difficult in like a normal Cal 2 class, is all the ways that all the different techniques we have to learn to go backwards. So this seems like a very big problem, all right? However, because there are two terms here and a single term here, we can split this into two fractions to start the problem. So let me just write it down and see if you agree with this. Is this not the same as u to the fourth over u squared minus 5, oops, let me move that up a little bit, minus 5u over u squared du. Isn't that the same thing? I'm putting it in parentheses because I've got two terms there now. Isn't that the same exact thing? That's just properties of fractions. Single term in the denominator, you can pull it apart. Okay? Now, what is u to the fourth over u squared? Just do some exponent stuff there. That's just u to the second power, u to the 2. So this is still, we want the antiderivative. We have u to the 2, and then minus, what about the next one? 5. This is u to the 1, right? So look at it this way. This u cancels, doesn't it? With one of those u's. So that 2 becomes a 1. So we just have a u on the bottom? Is that okay? You could bring it up as a negative 1,
That's what I wanted to do.
right? I heard you say negative 1. Now, I'm not going to, because wasn't u to the negative 1 the one special case we had to worry about?
Yeah.
So watch me write this one more way. U squared minus 5 times 1 over u. See, I'm going to write it that way. I think it's a little easier to see that 5 over u is 5 times 1 over u. So do you see why I don't like this notation as much as this notation? Because what is the antiderivative of 1 over u? Natural log of u, right? Because this is like 1 over x. So can you get the antiderivative of that? Yeah? Antiderivative of that, bring the negative 5 along for the ride, slap a c on the end, and we're there. So we've got 1/3 u cubed minus 5 natural log of u plus c. So notice that when I go from this step to this step, a bunch of these symbols disappear, don't they? Like this sign goes away, this little du, like just, my students always ask me, like, what happened to the du? So don't worry about it, but if you need it to go somewhere, it becomes the c, all right? Just, we go from this line to this line, that's the step where you're actually finding the antiderivative, all right? Questions? What if this would have been plus 1 down here? You could not do it this way where you would get this nice cancellation. In fact, that would be a tough problem even for my Cal 2 students to do. This one right here, this is a hard problem right there. It would take a lot of work. Right? So these problems that you might see in the book, they're going to be very special. You know, you might have multiple terms up here, but you'll always have a single term down here. That way you can split it. All right? How do y'all feel about this? We're going to do a word problem now. So let's say that the marginal average cost of producing X glasses thinking like sunglasses, okay, is given by this function. Also, the average cost at 100 sunglasses is, let's go with 40. The question is to part A, find average cost function. Part B, find cost function. And part C, find fixed costs. All right. Now, after everything we've done so far today, this seems like, whoa, where did this come from, right? Like doing this now, with all we've done is talked about antiderivatives. So let's take a look at what we've got. We have the marginal average cost function. That's what this is right here. This is the marginal average cost function. Marginal, that word basically tells us the derivative, okay? So this is the derivative of the average cost function. Does that make sense? If that marginal wasn't there, then this would be the average cost function. But because it says marginal, it means, hey, look, we're looking at the derivative of the average cost function. There it is. And then they also give you some information about the average cost function, not the derivative of it. See the derivative symbol? The average cost function at 100 is 40. All right. We need to find the average cost function, then the cost function, then the fixed costs. Let's just see what happens, all right? How can I find the average cost function? This is its derivative, right? So we need to take the antiderivative of this, don't we? Okay. So this step right here, what we're going to be doing is taking the antiderivative of the average cost function. Okay, that's what this step is going to be. Take the antiderivative of the average marginal average cost function. So let's try it. Let's do it. This is the antiderivative of, how could I rewrite that so that that looks more like a power of x?